Okay, section 12.5 is on phase diagrams. And we're just going to dive right into the figures here. Figure 12.25 shows a generic phase diagram. And let's look at these because they contain a lot of information and they're really interesting. On the y-axis here you have pressure, and on the x-axis you have temperature. And then instead of just like one curve like we're used to seeing, what you have is a number of curves that are enclosing different regions. Those regions are the different phases of matter. So if I pick a certain temperature and pressure condition, let's say my temperature is this cold and my pressure is this high, then you'll land in the region that denotes a solid. So your substance will be a solid at that given temperature and pressure. Of course, each substance is going to have its own phase diagram that will look different and be unique to that given substance. There's a number of really important things to notice here. So in between phases, like here's the solid phase, here's the gas phase, and here's the liquid phase. In between these phases are the lines where phase transitions can occur at equilibrium. So if I wanted to know what is the melting point at a given pressure, I would look for where this line is between the liquid and the solid phase. The temperature where that line falls is going to be the melting point. If I want to know the boiling point, then I would take that pressure and go find the curve which defines the boundary between liquid and gas, and the temperature where that curve lies would be the boiling point. So at 1 atmosphere, for example, we'll follow this dotted line across. That's the normal melting point, and the normal boiling point would be these temperatures. And at different pressures you'll have different melting and boiling points. If you move from left to right, then you're warming up the substance. So it makes a lot of sense that if I start as a solid up here at relatively high pressures and I increase the temperature, it will melt to form a liquid, and I continue to increase the temperature, eventually it will boil to form a gas. If I'm at a sufficiently low pressure, then instead of melting, we'll get sublimation directly from solid to gas. But you'll notice we can undergo phase changes at constant temperature by changing the pressure. So if I start as a solid and decrease the pressure, eventually the pressure gets low enough that you'll see sublimation into the gas phase. If I start as a gas and I increase the pressure here at higher temperatures, eventually that gas will be compressed down into a liquid, and we'll observe a phase change. It will begin to condense. There are also a number of important points on this graph. So along these lines where the phase transitions occur, you can have solid and liquid coexisting at equilibrium. Let's suppose I have a block of ice at 1 atmosphere of pressure, and I bring it up to 0 degrees Celsius. That's the normal melting point. If I bring it up to 0 degrees Celsius and I continue to add heat until about half of that ice has melted, but then I stop adding heat and I put it in an isolated chamber where it will stay at that temperature with no heat exchange and leave it for 10,000 years, when I come back and check on it, it will still be half ice and half liquid water because it's at equilibrium at that temperature. Likewise with liquid to vapor boundary, if I heat some liquid up to the boiling point and I boil half of it away, and then I isolate the system so that no heat is given or taken from it, and it remains at that temperature, then when I come check on it in 10,000 years, it'll be 50% liquid water and 50% water vapor. Well, there's one point right down here where the gas and liquid and solid boundaries share a common intersection, and that is called the triple point. This is the one set of conditions of pressure and temperature where all three phases of matter are allowed to coexist in equilibrium. And I like to use an analogy here. If I have a glass of ice water sitting out on my kitchen counter, then we have all three phases of water present. We have the ice cubes that are solid, we've got the water in the glass, and then there will be some water vapor up above the glass. But they are not coexisting at equilibrium. They're in a non-equilibrium state. If I leave for a few hours and come back, the ice will be melted. If I leave for a few weeks and come back, the water will have evaporated away. And so it's very much non-equilibrium. Well, if I had a glass of ice water that was at precisely the right pressure and temperature to put it at the triple point, then I could leave for 10,000 years and come back, and when I checked on it, there would still be the same proportions of ice and liquid water and water vapor, which is a pretty cool idea. So every substance has one set of conditions called the triple point, and you'll find it here at the intersection of all of our phase change boundaries. There's also a point up here in the upper right called the critical point. And the critical point is a little bit harder to explain or understand the reasons why it exists. But what it really amounts to is that above there we do not observe a phase transition between liquid and gas. Remember on the heating curves from section 12.3, you would add heat at a constant rate, and then once you reached a melting point or boiling point, you would see the temperature remain constant as the substance underwent a phase change. So that's how we can measure and observe a phase change. Well, above the critical point, there is no longer any observable phase change between the liquid and the gas. What you have is a supercritical fluid, and we call it that because we can't really reliably say whether it's a liquid or a gas. It's some new phase, a supercritical fluid. And it has a lot of the properties of both liquids and gases. Supercritical fluids are really useful in industry and in science because they have the solvating properties of liquids, but they have the compressibility of gases. They're really unique sorts of fluids. And what you can do is change the pressure or change the temperature and end up sort of clearly within either the liquid or the gas region without ever observing a phase change. So let's say I start here in the middle of the gas region. If I increase the temperature and then I increase the pressure and then I decrease the temperature and then I decrease the pressure so that I'm in the middle of the liquid range, I will have gone from something that is clearly and unambiguously a gas into something that is clearly and unambiguously a liquid without ever observing a phase change between the two, which is a pretty wild idea. So that's the basic anatomy of a phase diagram. You'll notice that the liquid-solid boundary is very steep, but it is not a vertical line. It's usually a positively sloped line, so it's usually going up and to the right ever so slightly. But there are exceptions to that rule, and we'll examine one in a moment. So if we look at this phase diagram, let's just answer these questions really quickly. What phases are represented in these regions? Well, the lowest temperature, high pressure phase is the solid. At really low pressures and high temperatures, that's a gas. and then the one in the middle is liquid. So C is solid, A is a gas, B is a liquid. Where's the line where the solid and the gas phases are in equilibrium? That will be this one that starts in the corner and curves up until it reaches the triple point. And what is the point indicating the normal boiling point? Well, we'll take the pressure of 1 atmosphere, we'll extend that across until we find that liquid vapor phase boundary, and then that is where the normal boiling point is. We could go down and see what temperature is on the x-axis to determine the normal boiling temperature. Okay, well, let's look at two different phase diagrams. Here we have carbon dioxide and on the left and water on the right. And both of these substances are interesting in their own ways. So for carbon dioxide, you'll notice the triple point is located up at a pressure of 5.11 atmospheres. And the liquid phase doesn't even exist below the triple point. That's why carbon dioxide will go from a solid directly to a gas under normal pressures. That's what dry ice is, solid carbon dioxide. And it's dry because when it's warmed up, it goes straight to a gas without any liquid. So that's one unique thing about carbon dioxide. But you'll notice its solid-liquid boundary line is slightly positively sloped. So if I start with a liquid and I increase the pressure, then eventually I'll cross over into the solid boundary. And that's how most substances are. It amounts to the solid being more dense than the liquid. If we come over here to water, however, that solid-liquid boundary line is negatively sloped. It goes up and ever so slightly to the left. And that's because the solid water is less dense than liquid water. And if I start at something just below the freezing point and 1 atmosphere of pressure, and I increase the pressure, then that will actually cause a transition to the liquid phase. You can melt ice by squeezing it, even if you keep the temperature constant, which is pretty interesting. Water also has an unusually large region of the liquid phase. You'll notice the temperature spans 300 Kelvin here, or 300 degrees Celsius or so on this graph. For carbon dioxide, you know, there is a region where carbon dioxide is a liquid at higher pressures, but you'll notice within just less than 100 degrees Celsius, you've pretty much already entered into the gas phase. So the liquid phase for water is particularly stable, and water exists as a liquid under a particularly wide range of conditions. Okay, so those are phase diagrams. Hopefully you can interpret them by, say, looking at a pair of temperature and pressure and identifying the phase that a substance will be in, identifying boiling and freezing, boiling and melting points at a given pressure, finding the critical point and the triple point, and I guess that's about it.